Hi boys and girls, Mr. Pancioli here. Welcome to your final lesson of the term. So, for this one, we're going to consolidate everything we've done so far in a quiz. Ideally, I'd like you to have a go at this without your fact books in front of you and without your notes in front of you. But by all means, if you're completely stuck, you're more than welcome to look through your notes if you need to. It's not cheating. It's a way of revision, so I don't mind that. But obviously, try for your own sake to see how much you remember. What we're going to do is I'm going to give you the questions on a slide. I'd like you to pause the video per slide. Take your time going through it. There's no rush. There's no time limit as such. And then the next slide is the answers. So what I suggest is you pause the video for a good enough amount of time so you can answer the questions in detail. You'll need a pencil, a pen, and a ruler for this. Okay, so let's make a start then. So, first topic is particle model. I'd like you to draw and describe the arrangement of particles in solids, liquids, and gases. And then I'd like you to describe the movement, the motion of particles in solids, liquids, and gases. Pause the video, spend a bit of time doing this. Okay. So for this, the answers you should have got are something along the lines of this. When we draw the solid, liquid, gas particles, always remember solid particles are in a neat, arranged pattern. They're all touching each other and they're all neatly arranged. You'll notice none of the dots are, and the yellow dots by the way represent the particles, none of the dots are overlapping. That's because in reality the particles are separate, they don't go into each other. So make sure yours don't overlap, please. In a solid, make sure it's completely full. In a liquid, you'll notice that they are still mainly touching, but in this case, they're not in an irregular pattern. In a gas, they are not touching at all, they're far apart, and they're spread out randomly. So how would you describe that? Well, in a solid, particles are all in a regular pattern, they're all touching and they're in a fixed position. In a liquid, there's irregular arrangement of particles. They are still touching. In a gas, all the particles are far apart. Number 2, movement of particles. In a solid, you'll see there's no space for them to move. So in a solid, particles are in a fixed position where they can vibrate only. Solid particles, liquid particles, gas particles always have kinetic energy. They're always moving as such. When you give them energy, they move faster. So in a solid particle, they can only vibrate on a fixed position. When you heat them up, you give them energy, they vibrate faster. In a liquid, because they're still touching, they can only move over each other. A common thing that students get wrong is they say liquid particles can move randomly. They can't. Liquid particles can only move over each other. In a gas, they are free to move wherever they want. They're not constrained, they're not touching. So in a gas, the key words to use are gas particles move, random directions, random speeds. Please correct anything that you didn't quite get right or add any information you need to, and we'll move on to the next part of the quiz. This is about density. Read the questions carefully and have a go at this. This one will require a bit of time and a bit of thinking. So pause the video and have a go at this, please. Okay, so for your density quiz, these are the answers you should have got. Density is mass divided by volume. Mass is always measured in kilograms. It's the amount of material inside something. And volume is always measured in meters cubed. It's the amount of space in a 3D object. Okay, you'll notice the 3 is higher up in the M. It's because it shows it's meter cubed. Density is kilograms per meter cubed. Slash means per. In a dense material compared to a not dense material, the particles are closer together. What that means is, because the particles are closer together, you fit more particles in the same amount of space. More particles means more mass. Same space means volume. So you have more mass in the same volume you've got bigger density. When a gas is compressed, the particles are brought closer together. That means if you continue to pump gas in and compress it, you're bringing the particles closer together, so there's more particles, or there are more particles in the same volume. Density increases when something is compressed. Now next one is the required practical. So think about this carefully. All three of these require you to find the density. And density is always mass divided by volume. So for each of these, anytime you get a density question, you always need to show how you find the mass and how you find the volume. That's the two important things. How you find the mass is always the same. You always use a set of scales to find the mass in grams or kilograms. That's it. You get a mark for saying that. Well, how you find the volume is what changes. So in a solid, regular object, that's like cuboids or cylinders or spheres or whatever, anything where you can easily measure the dimensions, you find the mass on the set of scales, you find the volume using a ruler to measure the dimensions. If you have a cuboid, it's height times width times length. If you have a cylinder, it's pi r squared times height, and so on. You must then write density equals mass divided by volume. That's an easy one. What about an irregular object like a lump of rock or a statue? You can't easily find the volume using a ruler because the dimensions are all different. You can still find the mass using scales, record that in grams or kilograms, but what you use here is something called a displacement can. Fill the can to just below the spout with water. Some water will spill out, that's fine. The can is then set on a table and settled. You'll gently lower the object you want to find the density of into the displacement can. The water level inside will rise. Some of the water will fall out. You'll have placed a measuring cylinder beneath the spout. The water that's displaced falls into the measuring cylinder, and the volume of the water is the volume of the object. So you found the mass, you found the volume. Density equals mass divided by volume. For a liquid, it's both easy and a bit weird at the same time. You'd start with an empty beaker or measuring cylinder and you put it on a set of scales. You don't record that unit, you just press 0 or tare. What that does is it resets the scales and sort of ignores the mass of the beaker or the measuring cylinder. So with the measuring cylinder on there, the scales will now read 0. What you then do is you fill that beaker or measuring cylinder with the known volume of liquid. That's your volume. And as you fill it up, the mass of it is shown on the scales. So you now have the mass of the liquid, the volume of the liquid, density equals mass divided by volume. And that is it. Add any information you need to, correct any mistakes, and we move on to the third part of the quiz. So this one's about internal energy. Some of it is copy and complete. Please do take your time again on this. Pause the video. Okay. Internal energy is talking about the energy inside an object. It's not about the object itself. So for example, if you think about a football, it's not about the movement of the whole football, it's about a movement of the particles that make the football up. In a solid, liquid and gas, those particles are always moving. So internal energy is made up of the kinetic energy of the particles plus the potential energy of the particles. Potential energy is due to their position and their bonds. When a system is heated and temperature is rising, internal energy is increasing because the kinetic energy of the particles increases. We're giving energy to the particles, which is making them move faster. That's increasing the temperature. When a system is heated and the object changes state, internal energy increases because the potential energy of the particles increases. We're breaking the bonds and the intermolecular forces. So energy in a change of state doesn't go into making the particles move faster. It goes into making the particles move further apart. It's changing the state. Sometimes changes of state happen. So a solid to a liquid, for example, an ice cube out on the table, it melts. If you continue heating it, the water, for example in a kettle, boils into steam, so it's boiling, gas. Sometimes you get a change of state where a solid goes straight to gas, leaving out the liquid state altogether. That's called sublimation. It's very rare. On the other hand, if we cool things down, if we start with a gas, which is very hot, and you cool it to a liquid, that's condensation. You might see that in the shower, for example. When the steam in the shower hits the cold window, it turns droplets of water. That's condensation. If you continue to cool the liquid, for example, if you put liquid water in an ice cube tray and put the ice cube tray in the freezer, it freezes. So liquid going to a solid, freezing. You can also get a situation where you can go straight from gas to solid, missing out the liquid stage again. That's called deposition. Very rare again. Change of state is a physical reaction because nothing new is formed. No new chemicals are formed. For example, if you got an ice cube is made of water. If you leave it on the table, you get liquid water. You've not made any new substances. You haven't made any new chemicals. It's still water. It's just the physical state of it is changing. So it's a physical reaction, not a chemical reaction. Whenever we get change of state, we always get the same mass. 1 kilo of ice will melt into 1 kilo of water. So there's no mass being lost or gained. Change whatever you need to, correct whatever you need to, and move on to the next part of the quiz. Specific latent heat. Now this one, take your time. You'll need a ruler, a pencil for this one. Please do as much detail as you can. And don't forget to pause the video if you haven't done so. Okay, so we're going to do this over a couple of slides. We'll do 1 and 2 over a slide each, and then 3 to 6 over one slide. So as the temperature graph, so you'll notice here the object is being heated up. As it's heating, its temperature is going upwards. This always a stepped increase whenever we heat something. So what you get is the first part. When I've noticed a mistake here, pause the video for a second. Let me just correct the mistake. Okay, that's better. So we start with a solid. Solid's heating up. When the solid heats up, its temperature increases. We can see it's going from -40 up to 0. Then there's no temperature change. It's changing state. On the flat part, it's melting. So we get a mixture of solid and liquid. At the end of the flat part, it's all liquid, so the liquid's temperature rises as it's heating up. It then reaches its boiling point, where it's a flat part, changes state, and it's boiling. It's all turning to gas. As it's all turned to gas at the end of the flat line, the gas begins to heat up. Once all the liquids turn to a gas, the gas's temperature continues to rise. So add any information you need to your graph, and we'll move on to the next slide. So in this one, we're cooling the substance down. You can see on the axis we start at a high temperature, 140, and we work our way downwards. So in this case, the gas is cooling. It then reaches a point where the gas is cool enough to begin to form a liquid. So that's condensation, change of state. Once all of the gas is turned to a liquid, the liquid begins to cool down. As it's cooling, it reaches a temperature, which is its freezing point. All the liquid begins to turn to a solid, and the solid then begins to cool down. Again, stepped process going downwards. During the flat parts, we've got change of state. We can see that on the graphs. We've got freezing and condensation, melting and boiling. It's where the change of state happens. The flat part between a liquid and a gas is longer because we need more energy to break the intermolecular forces. Gas particles need to be completely far apart. So we need more energy. More energy means more time. Specific latent heat, amount of energy needed to change the state of 1 kilo of something without changing its temperature. Latent heat of fusion is the amount of energy needed to melt 1 kilo. Latent heat of vaporization, amount of energy needed to boil 1 kilo. An equation for specific latent heat, energy equals mass times specific latent heat. And this equation works for both latent heat of fusion and latent heat of vaporization. Thank you, boys and girls. You've been awesome. Well done. All the best. Bye, guys.